Wana Gama dibangun dengan spirit yang menjulang tinggi pada tahun 1960-an. Pada saat itu, dengan kondisi sumber daya manusia dan teknologi yang terbatas, serta finansial yang lemah, mampu memulihkan hutan dan lahan kritis di Gunung Kidul. Universitas Gadjah Mada melalui Fakultas Kehutanan mengabdikan diri melalui Tridharma Perguruan Tinggi. Terbangunlah Hutan Pendidikan Wana Gama.
Hutan Pendidikan Wana Gama adalah hutan pendidikan yang dimiliki oleh Fakultas Kehutanan UGM seluas 625,25 hektar yang merupakan hutan pendidikan yang dibangun mulai dari lahan kritis, sekarang telah menjadi hutan yang hijau dengan segala macam fungsinya, baik untuk penyedia oksigen, air, tempat rekreasi, dan juga tempat pendidikan.
Wana memiliki makna hutan dan Gama memiliki kepanjangan dari Gajah Mada. Wana Gama merupakan karya Universitas Gadjah Mada melalui mengukir alam dengan rehabilitasi lahan kritis.
Wana Gama itu dibangun dengan spirit yang sangat jelas, rehabilitasi lahan kritis untuk kesejahteraan masyarakat dan rehabilitasi lahan kritis untuk penyelamatan lingkungan. Model ini sudah selayaknya dijadikan sebagai contoh untuk rehabilitasi lahan kritis di Indonesia yang saat ini luas lahan kritis lebih dari 40 juta hektar.
Wana Gama telah menjadi rujukan rehabilitasi hutan dan lahan kritis, dan saat ini spektrumnya terus meluas tidak hanya di Gunung Kidul, kawasan Geopark Gunung Sewu, namun juga Indonesia dan bahkan dunia. Hutan Pendidikan Wana Gama saat ini dikelola secara profesional oleh Sivitas Akademika Fakultas Kehutanan Universitas Gadjah Mada melalui unit pengelolaan Wana Gama.
Pengelolaan Wana Gama terus menjunjung tinggi spirit perjuangan Wana Gama, sehingga Wana Gama menjadi sumber inspirasi dalam proses berpikir dan sebagai tempat belajar mengolah ekosistem alam. Salam Wana Gama, salam harmoni kehidupan dengan alam.
Kegiatan pendukung Tridharma Perguruan Tinggi di Wana Gama antara lain kebun pembibitan, percontohan budidaya ulat sutra, dan museum kayu. Kegiatan di Wana Gama sebagai rujukan rehabilitasi hutan dan lahan kritis antara lain pendidikan, pelatihan, penelitian, dan pengabdian masyarakat. Wana Gama sebagai hutan pendidikan digunakan sebagai kampus lapangan dalam mendidik mahasiswa Fakultas Kehutanan Universitas Gadjah Mada. Pelatihan-pelatihan yang dilaksanakan di Wana Gama diikuti oleh peserta dari dalam maupun luar negeri. Jati Mega merupakan salah satu buah karya penelitian yang dilaksanakan di Wana Gama. Wana Gama juga memfasilitasi masyarakat umum yang ingin menggunakan kawasan Wana Gama untuk kegiatan wisata alam. Penginapan yang sangat memadai sudah tersedia di Wana Gama. Masyarakat dapat menikmati kenyamanan fasilitas penginapan di Wana Gama dengan harga yang sangat terjangkau.
Yayasan Umi itu maksudnya itu untuk membackup pengelolaan Wana Gama. Dia memesankan kepada kita semua untuk supaya tidak meninggalkan Wana Gama, maka dibuatlah Yayasan Umi yang pertama kali modalnya kita peroleh dari Bu Umi sendiri dan dari saudara-saudaranya dan dari beberapa orang yang lain. Kemudian didirikanlah Yayasan Umi. Selama ini kami hanya membantu bagaimana melancarkan pekerjaan-pekerjaan teknis di Wanagama. Kami juga bisa mengatur supaya dana itu tidak habis ya, biar bisa berkembang. Jadi kami tetap akan berada di Wanagama untuk sesuai dengan pesan dari almarhumah yang menjadi perintis dari Wanagama.
Bagi masyarakat yang memiliki hobi bersepeda, dapat mencoba wisata bersepeda mengelilingi hutan Wanagama. Untuk memperoleh tantangan yang lebih ekstrim, pesepeda dapat mencoba trek khusus bersepeda di Wanagama. Dalam upaya menumbuh kembangkan spirit Wanagama kepada generasi Indonesia, maka Wanagama diarahkan sebagai Eco-Edu Forest. Salah satu upaya awal untuk menginisiasi Wanagama sebagai Eco-Edu Forest yaitu dengan melakukan pengembangan program Wanagama 1000 Selfie atau WG1000S. WG1000S sebagai wahana untuk menyebarluaskan spirit Wanagama lintas generasi sebagai bagian penting dari pendidikan lingkungan dan upaya berkelanjutan untuk menjaga kelestarian ekosistem sumber daya alam.
Universitas Gadjah Mada, bring ideas to life and make a difference. As an inclusive university, we believe in a world-class education system for all. From the struggle and courage of the Indonesian Revolution for Independence, we started a journey to build the nation. We have since laid the foundation for lifelong learning that extends across generations. As we face rapid cultural and technological shifts, we understand that staying one step ahead of challenges is the way forward. Innovation and transformation are integral to every move we make, including how we deliver education. In response to industry challenges, we are always open to feedback and collaboration. We translate research on food security, sustainable energy, net zero healthcare into useful products and formulate solutions to societal needs and problems, as seen from our role and contribution to tackling the COVID-19 pandemic. Our new, ever-developing infrastructure with a variety of supporting systems and modern technology is built to accelerate the pursuit of answers while making everyone feel at home. Through our focus on food, health, and energy, we join hands to make the world a better place now and into the future. Here at UGM, passions are nurtured beyond academic fields. The facilities that cater to their needs, students are given the space to unlock their potential, unleash their creativity, and reach for the stars. Our dedication to community development reaches far and wide to every corner of the archipelago and those closest to us. We synergize and share roles with various stakeholders to build an empowered and resilient community. Our commitment to serving the interests of the nation and humanity has led us to pick up achievements and awards at the individual, group, and institutional levels on the national and international stages. Unity in diversity. We push knowledge forward and make a high community impact that matters in harmony with our long-held principle, globally respected.
We are UGM.
Wanagama dibangun dengan spirit yang menjulang tinggi pada tahun 1960-an. Pada saat itu, dengan kondisi sumber daya manusia dan teknologi yang terbatas, serta finansial yang lemah, mampu memulihkan hutan dan lahan kritis di Gunung Kidul. Universitas Gadjah Mada melalui Fakultas Kehutanan mengabdikan diri melalui Tridharma Perguruan Tinggi. Terbangunlah Hutan Pendidikan Wanagama.
Hutan Pendidikan Wanagama adalah hutan pendidikan yang dimiliki oleh Fakultas Kehutanan UGM seluas 625,25 hektar yang merupakan hutan pendidikan yang dibangun mulai dari lahan kritis, sekarang telah menjadi hutan yang hijau dengan segala macam fungsinya, baik untuk penyedia oksigen, air, tempat rekreasi, dan juga tempat pendidikan.
Wana memiliki makna hutan dan gama memiliki kepanjangan dari Gajah Mada. Wanagama merupakan karya Universitas Gadjah Mada melalui mengukir alam dengan rehabilitasi lahan kritis.
Wanagama itu dibangun dengan spirit yang sangat jelas, rehabilitasi lahan kritis untuk kesejahteraan masyarakat dan rehabilitasi lahan kritis untuk penyelamatan lingkungan. Model ini sudah selayaknya dijadikan sebagai contoh untuk rehabilitasi lahan kritis di Indonesia yang saat ini luas lahan kritis lebih dari 40 juta hektar.
Wanagama telah menjadi rujukan rehabilitasi hutan dan lahan kritis, dan saat ini spektrumnya terus meluas tidak hanya di Gunung Kidul, kawasan Geopark Gunung Sewu, namun juga Indonesia dan bahkan dunia. Hutan Pendidikan Wanagama saat ini dikelola secara profesional oleh Sivitas Akademika Fakultas Kehutanan Universitas Gadjah Mada melalui unit pengelolaan Wanagama.
Pengelolaan Wanagama terus menjunjung tinggi spirit perjuangan Wanagama, sehingga Wanagama menjadi sumber inspirasi dalam proses berpikir dan sebagai tempat belajar mengolah ekosistem alam. Salam Wanagama, salam harmoni kehidupan dengan alam.
Kegiatan pendukung Tridharma Perguruan Tinggi di Wanagama antara lain kebun pembibitan, percontohan budidaya ulat sutra, dan museum kayu. Kegiatan di Wanagama sebagai rujukan rehabilitasi hutan dan lahan kritis antara lain pendidikan, pelatihan, penelitian, dan pengabdian masyarakat. Wanagama sebagai hutan pendidikan digunakan sebagai kampus lapangan dalam mendidik mahasiswa Fakultas Kehutanan Universitas Gadjah Mada. Pelatihan-pelatihan yang dilaksanakan di Wanagama diikuti oleh peserta dari dalam maupun luar negeri. Jati Mega merupakan salah satu buah karya penelitian yang dilaksanakan di Wanagama.
Good morning, good afternoon, good evening, everyone. Be informed that the official virtual background for this webinar has been provided in the chat box. You are encouraged to use it. Oh, kurang. Tes, 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 tes. Kurang. Tes, tes. Good morning, good afternoon, good evening, everyone. Kindly be informed that official virtual background for this webinar has been provided in the chat box, and you are encouraged to use it. And the webinar will be beginning in approximately 4 minutes. And so please stay tuned. Thank you for your kind attention.
Check, check. Can you hear my voice? Thank you very much for the attending this event, Professor Hiroyuki Yamamoto, Professor Yusef Grill, Professor Imam Wahyudi, Professor Sri Nugroho Marso, and many researchers here. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, greeting to all of us. Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, greetings to all of us. Good morning, good afternoon, and good evening, ladies and gentlemen who are joining us from various countries around the world, including Japan, the United States, Asia, the United Kingdom, Sweden, Switzerland, France, and many others. Welcome to the first session of the webinar series 2025, brought to the 11th International Plant Biomechanics Conference 2026. Allow me to introduce myself. My name is Sheldon Adelma, and I'm honored to serve as your Master of Ceremony for today's webinar. Before we proceed, may we kindly remind all participants of official virtual backgrounds provided in the chat box. It's a great honor for me to inform you that today we are joined by distinguished speakers. Professor Dr. Hiroyuki Yamamoto from Nagoya University, Japan. Associate Professor Miyuki Matsuo Ueda from Kyoto University, Japan. Mr. Razaka Noviandi, PhD from Universitas Gajah Mada, Asia. And also Mr. Jeffrey Indra Huta Barat, MSc, Asia Pacific Resources International Limited, April, Indonesia. This webinar is proudly organized by the Faculty of Forestry Indonesia and Universitas Gajah Mada, part of our journey toward the 11th International Plant Biomechanics Conference, which will take place in Yogyakarta, Asia on August 23 until 28, 2026. In today's session, we will explore the fascinating field of plant biomechanics, focusing on how trees and forests respond to mechanical challenges from growth, stresses at tree trunks, to the role of forest density in slope stability, and even how wind damage can be modeled in eucalyptus plantation. We are truly honored to have you all here today to share knowledge, exchange insight, and strengthen collaboration in exciting scientific field. Ladies and gentlemen, allow me to inform you for our agenda for today. For the first agenda is the opening session. The second agenda is the welcoming remarks by Professor Dr. Widianto Dwi Nugroho, Chair of the 11th International Plant Biomechanics Conference 2026. The third agenda is the introduction about plant biomechanics by Prof. Dr. Hiroyuki Yamamoto from Nagoya University, Japan. The fourth agenda is the first presentation by Associate Professor Dr. Miyuki Matsuo Ueda from Kyoto University, Japan. The fifth agenda, the second presentation by Dr. Razaka Noviandi from Universitas Gajah Mada, Indonesia. The sixth agenda is the third presentation by Mr. Jeffrey Indra Huta Barat, MSc, from Asia Pacific Resources International Limited, April, Indonesia. The seventh agenda is the question and answer session. And the last agenda is the closing session. Ladies and gentlemen, moving on to the next agenda, we are truly honored to have with us Professor Dr. Widianto Dwi Nugroho, the chair of the 11th International Plant Biomechanics Conference 2026. We would now like to kindly invite Professor Dr. Widianto to deliver his welcoming remarks. Professor Dr. Widianto Dwi Nugroho, the floor is yours.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, distinguished speakers, colleagues, and participants, on behalf of the organizing committee, it is our great pleasure to welcome you to the first webinar series 2025 brought to the 11th International Plant Biomechanics Conference next year, 2026. This webinar series is organized by Department of Forest Product Technology, Faculty of Forestry, Universitas Gadjah Mada, Yogyakarta, in Indonesia. This webinar has been created as a forum for sharing and discussing the various work in this field. Through a series of online sessions, the program will feature research presentation and applied case studies from experts, young researchers, and practitioners worldwide. The series is open to researchers, academics, students, and practitioners who are interested in deepening their understanding of plant biomechanics and its real-world application. On behalf of the organizing committee, I extend my warmest greeting to all speakers, researchers, academics, practitioners, students, and participants who have joined us. Your presence here reflects our shared commitment to bridge plant biomechanics and engineering for sustainable solutions as the topic of the 11th International Plant Biomechanics Conference 2026. We are honored to welcome Professor Hiroyuki Yamamoto. Konnichiwa, Yamamoto Sensei.
Konnichiwa.
And also Professor Dr. Miyuki Matsuo Ueda from Kyoto University, Mr. Rosdaka Noviandi, PhD from Universitas Gadjah Mada, and also Mr. Geoffrey Indra Huta from April, Indonesia, as our speakers who will deliver an insightful address line with our theme of this seminar. As part of the road of the 11th International Plant Biomechanics Conference 2026, this webinar series is more than scientific forum. It is also a community building effort. It connects researchers across continents, strengthens international networks, and encourages the next generation to engage with plant biomechanics. This event has successfully gathered more than 200 participants from several reputable universities and institutions from more than 10 countries. At the same time, this series also serves as an open invitation to participate in the 2026 conference on August next year. Finally, I wish you an engaging seminar and awesome experience. May the discussion enrich our insight, strengthen our network, and contribute significantly to bridge plant biomechanics and engineering for sustainable solutions. And we are looking forward to seeing you on the second webinar on 9 October 2025. Thank you very much for your kind attention and participation. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Professor Dr. Widianto Dwi Nugroho, for your warm and inspiring welcoming remarks. Ladies and gentlemen, now it's time to move on to the next part of our program. We are excited to be guided today by a truly remarkable moderator. She is an inspiring academic excellence discussion leader from Universitas Gadjah Mada, Dr. Fani Hidayati. Dr. Fani Hidayati, with bachelor degree at Faculty of Forestry, Universitas Gadjah Mada, Master degree Faculty of Forestry, Universitas Gadjah Mada, doctoral degree UGAS Tokyo University of Agriculture and Technology. She also published numerous international journals, and her current position as Associate Professor, Faculty of Forestry, Universitas Gadjah Mada, Indonesia. With her experience and expertise, I'm sure today's session will run smoothly and engagingly. Dr. Fani Hidayat, the floor is yours.
Thank you very much, Mrs. Celine, for the time. Good afternoon, ladies and gentlemen, speakers, plant biomechanics boards, researcher, academics, lecturer, and student, and all respected webinar participants. Assalamualaikum warahmatullahi wabarakatuh. Welcome to the webinar series 2025, Road to the 11th International Plant Biomechanics Conference 2026. It is an honor for me, Fani Hidayati, to lead this very special session of this webinar. Today is the first webinar of the two webinars before the offline conference of the 11th International Plant Biomechanics Conference 2026. This conference serves as a gathering for researchers around the world to share knowledge on the biomechanics of plants, fostering collaboration and the exchange of ideas in the field. This is the first time that this conference will be held in Yogyakarta, Indonesia on next year. However, this webinar is the preliminary session of that conference. In this webinar, we would like to present research about plant biomechanics, especially in Asia. In this session, we will have 4 expert and highly competent speakers in their fields. Let us extend a warm welcome to the speakers. First, Professor Dr. Hiroyuki Yamamoto from Nagoya University, who will present the introduction to plant biomechanics. Good afternoon, Professor Yamamoto. And the second, Associate Professor Dr. Matsuo Ueda from Kyoto University, Japan, who will present about recent research on crude stresses in trees, the unique residue stress distribution in Zelkova serrata. Good afternoon, Dr. Matsuo Ueda. And the third, Mr. Rozaka Noviandi, PhD from Universitas Gadjah Mada, Indonesia, with a presentation on effect of forest density on slope stability insight from flume experiments. Good afternoon, Dr. Rozaka. And the last speaker is Mr. Kefri Indra Huta Barat, Master of Science from Asia Pacific Resources International Limited, Indonesia, who will share findings on parameterization validation on the forest scales model to define the critical wind for damage and of different eucalyptus clone. Good afternoon, Mr. Kefri. Ladies and gentlemen, to ensure the smooth running of this session, we will allow approximately 15 minutes for each speaker to deliver their presentation. This will be followed by interactive question and answer session between participants and speakers for about 20 minutes. Before we start for the first presentation, I would like to introduce Professor Dr. Hiroyuki Yamamoto.
Okay, thank you. Thank you very much for introducing me to the participant of the webinar. Okay, sorry. Not yet started.
Okay, yeah. Thank you.
Can I start? Not yet?
Yes, not yet. I'm sorry.
Not yet. Okay, sorry. I'm sorry.
Okay, yes.
No.
Okay. Professor Yamamoto is a professor of the School of Bioagricultural Science in Nagoya University, Japan. He has 2 degrees of doctoral philosophy in agriculture from Nagoya University and PhD in engineering from University of Yamanashi, and also did postdoctoral in Brazil. Research focus in strain analysis, residual stress, growth stress, reaction wood, and also he has produced many of international publications. Without any more time, let us begin this session by listening the first presentation about introduction to plant biomechanics. Please welcome Professor Yamamoto to start the presentation. Please, Sensei.
Okay, thank you very much for introducing me to the participant. Can I share my files like this one? Like this. And just a moment, sorry. やるんだ、これ。スライドショーで、 Okay, let's try to start.
Yeah.
The title of my presentation is this one, Plant Biomechanics. What do we have to learn from plants? As the first speaker of this webinar, I would like to introduce the plant biomechanics. And I engaged in almost 10 years ago, 2015. We had a plant biomechanics conference in Nagoya, Japan. This is the 8th PBM conference, and I worked as one of the chair. And I am a wood scientist. So from my insight, I introduce my plant biomechanics, my plant biomechanics, focusing on my interest. The content of the presentation consists of 3 chapters. The first chapter is where do plants come from and where are we going? History of plant evolution. And the second chapter is plants understands physics and use it to survive for long evolution. And the last chapter is where our PBM should go and learn. So from my first chapters, plants grow higher than 100 meters and bigger than 2,000 tons, and can survive more than 5,000 years, as you know. And the plant has aimed solely at growing mammoths since its first appearance on the Earth. By the way, why plants must become mammoths against such a cruel gravitational stress? Very heavy, very, very big and very heavy. And their motivation are how to survive the struggle for existence. And to become mammoths is very important strategy to get a better living place for their photosynthetic activity. As a consequence of the long-term evolution and struggle for existence over than 500 million years, the forests of all sizes have appeared and spread everywhere on the earth, like this canopy structure of the Amazonian natural forest, with high diversity of the creatures and the animals and the plants. So from this slide, I will explain the deepest history of plant evolution. In the hidden eon of the planet Earth, this one, ocean is cradle of ancient life, about 4,000 million years ago. And we had the occurrence of the live materials, RNA, DNA, or amino acid or protein, we don't know. Still, we don't know. And this one, after a long time later, first life evolution advanced in the sea. This one, pre-Cambrian age. And the early Paleozoic era, the first land plant started from primitive green alga. Okay, this one is very famous ancient plant, Cooksonia peltoni in England. Okay, 420 million years before, the size is very tiny, very small, no vascular bundles, having a spore case like this, and a forky. So this is the landscape of the Cooksonia ecosystem. The struggle for existence has just started in the ancient Stark ecosystem of Cooksonia. Very simple landscape near the water. The key to survive is to evolve vascular bundles. and the early Paleozoic era, still Paleozoic. Soon they evolved vastly abandoned 400 million years before, having an acquisition of structure, axial structure like this. Lignified cell becomes the key to develop the systems of water transport. This one is very important to become big. And also mechanical support of the land plant. This is also very important functions. And the mid-Paleozoic era, this one is the landscape of the Paleozoic era. And this one, many plants already evolved. Fern forest appeared 350 million years ago, like this. And the reptile flora developed from fish. They soon developed into dinosaurs and the mammals in Mesozoic era. Plant diversified dramatically, grew many kinds of plants already, and the enormous sizes, very big. For example, 50 meters, and formed Paleozoic forest, like a forest of palm forest, Perun palm forest. And this one is the Mesozoic era, the gymnosperm developed into the modern conifer, like this, and some developed into the angiosperm at Kenozoic era. This one is a hard word, Japanese beach. The modern Kenozoic era plant system. This one is a modern canopy structure of the Amazonian natural forest, Manaus, Brazil, with a high biological diversity. The tropical forest is a laboratory of a large-scale evolutions. Long-term evolution has forced plants to become mammoths to survive the struggle for existence. Those are called forest. We developed forestry from forest. Another strategy is neoteny. Neoteny, which is called herbaceous plant or crop. This one is directly related to the agriculture. Evolutions are still going on now. Here, our plant biomechanics can learn from evolution. Just sorry. Okay. So next chapter is the plants understand physics and use it to survive. And the plants understand physics and use it to survive. How the tree can support the big body. Key to answer this question are the one, a well-designed structure of the cell wall and the xylem. The second is the mechanical control of tree shape, plant shape, by the reaction wood and the growth stores. The third topic of this chapter is water transportation system based on water physics. Plant utilizes those mechanics and the physics for their survival. Okay, this one is a well-designed structure of the cell wall and the xylem structure. Properties, features, spatial arrangements of the component of the skillfully optimized in the wood cell wall with controlling the well-designed cell shape. And this one, cellulose microhebule, as a rigid framework and a matrix substance consisting of lignin and hemicellulose as a matrix. What should we learn something from it is very important in our future investigation. And the second, the mechanical control of tree shape by the reaction wood under growth stress. You can stay on your feet with arms spread so many years against the heavy wind and rain. The tree performs this hard work with their own muscle building technique, that is a growth stress, as well as the formation of reaction wood. Trees have invented their own muscle building technique to control their huge body. That is a generation of growth stress in reaction with fiber. The topics of the growth stress will be explained by the next speaker, Dr. Matsuo from Kyoto University. And what should we learn about it? Okay. How is herbaceous plants? The growth stress of the herbaceous plant, we have less knowledge yet. And the last topics of this chapter is water transportation system based on water physics. How does water rise to the height of 100 meters? Very tall. The previous models, this one, were incomplete or misleading, but for example, pumping by vacuum pump and capillary rise theory or pushing by root pressure or others. Those theories now we know they were incomplete or misleading. But now we learn the water potential theory explains the mechanism of water rising. But is it completely true or not? Not yet finally decided. How should we learn and develop it? So we move to next chapters. Okay. The last chapter is where our PBM should go and do. The plant biomechanics, our way to learn, our way to know. For example, plant biomechanics consists of many fields and topics. Maybe main field is tree and herbaceous and the cell wall and the cell wall molecules. Tree, herbaceous plant, and the cell, living cell, and the cell wall, and the cell molecules. And about the tree, of course, tree science, this adopt well applying mechanics and physics. But enough or not in future? Is it true? Is it a proper? But lesser applying the molecular mechanism. This is a problem of tree mechanics and the tree physics and tree biomechanics. And about the herbaceous plant, this one is based on the molecular biology, where developing the molecular sciences. Many knowledge, many development in the 20th centuries and the 21st centuries. But lesser applying mechanics, especially theory, mechanical theory and the physical theory, and the cell and molecules. Of course, this one is also the science of materials and the biologies, both fields, where developing analysis they have, and they accumulate knowledge in concert effect of the physics and the chemistry. But the lesser standpoint of macroscopic synthesis, this one will be very important, I think. And tree, herbaceous plant, and the cell and the molecules, those plant biomechanics. The plant biomechanics are already very developing and very accumulating the very important scientific knowledges in 20th centuries and the 21st centuries. But the purpose and knowledge about the plant biomechanics will go to play them. We still find out the answer to those questions. Okay, thank you very much. I finish my presentation. Thank you very much for patience. And I pray the plant biomechanics to develop more and more and in future and become a very important science for human beings. Thank you very much.
Thank you very much, Professor Yamamoto, for the sharing knowledge about the plant biomechanics from the history of the evolution until the very important of the plant biomechanics today. Okay, and we will move to the presentation. We would like to enter the second presentation by Associate Professor Dr. Miyuki Matsuo Ueda. I would like to introduce Dr. Matsuo Ueda. She finished Bachelor, Master of Science, and Doctor Philosophy from Kyoto University. She is now Associate Professor in Graduate School of Agriculture, Kyoto University. And her research interest is about natural aging of wood, thermal treatment of wood, growth residual stress of trees, biomechanics, the relationship physical properties of wood, and traditional woodworking. And she already have many international publications in the topic of her interest. And we invite Dr. Matsuo Ueda to give presentation with the title Recent Research on Growth Stresses in Trees, the Unique Residual Stress Distribution in Zelkova serrata. Dr. Matsuo Ueda, time is yours.
Thank you for introducing about me. Could you check my slide? Is it okay?
Yes, okay.
Okay, thank you. Thank you for coming to this webinar. And I'm Miyuki Matsuo Ueda from Kyoto University, Japan. So it is a great honor to make the presentation on the first day this webinar. Thank you for giving this wonderful opportunity. Today, I'm going to talk about our research progress on growth stress of trees, especially findings on the unique distribution of residual stress in Zelkova serrata, namely Japanese Zelkova. So I'm a staff of Kyoto University, which is located in the western part of Japan. You may know about Kyoto as a historical place where there are a lot of old and traditional wooden buildings of shrines, temples, and houses. So here is a photo of a temple. Name is Chionji Temple, which is close to Kyoto University. The main building is built with Japanese Zelkova wood, which is today's materials. You can see here, not this beautiful cherry blossom. So Japanese Zelkova is one of the major hardwood species in Japan, especially used for traditional buildings, furniture, and sculptures. Zelkova trees have large straight stems, like here, and its wood has a good appearance with dynamic pattern and dark yellow color. Through our collaboration research with a traditional construction company to understand the characteristics of Zelkova wood, we found unique points of Zelkova trees from the viewpoint of plant biomechanics. So I would like to talk about these findings today. Here is a fundamental description of residual stress of tree. tree have internal mechanical stress in their trunks that is called residual stress. Other name is growth stress. The image in the middle is the normal status of the tree residual stress. There are tension stress in outer side of a stem and compressive stress around the piece, with a gradient from surface to piece. So it is said that the effect, good effect of residual stress is the tensile press stress of outer side reduces the surface compression when the vertical load such as wind is added on tree. This press stress finally protects tree from buckling in the inner side of the bending due to wind or something. But the residual stress is released by cutting trees or logs, and it makes wood deformed. Here are some examples of the deformation due to the release of residual stress. These deformations reduces the economic values of logs. So the residual stress of trees have been of interest of scientists in the field of forestry and wood science. And the scientists try to develop the way to quantify the residual stress. Here I will explain about the method to measure residual stress. Measurement of residual stress uses deformation of wood. Here is an explanation of conventional way. A thin board, including the piece of a tree, is cut from the log. And then the board is cut into many narrow strips. The curvature of these narrow strips or deformation of strips can be an indicator of the magnitude of residual stress. And finally, you can get such a graph showing the distribution of residual stress. So several methods have been developed as listed here. So we employed the strain gauge method, which makes us to do the high throughput measurement. So residual stress is represented by released strain and recorded as the distribution of stress along with the horizontal line from the piece to back side of the tree trunk. Here is an example of obtained data. So you can see positive large strain around the piece, which represents the compressive mechanical stress, and negative strain at back sides, both back sides, which represents tensile stress. So from this slide, I'm going to use this released strain, not stress, released strain as an indicator of residual stress. So here I will show the distribution of released strain of some wood species, Japanese softwoods, acacia mangium, palcata, teak, and Japanese cerocoba. So there are some differences in the steepness of this bell shape. This kind of smooth bell shapes distribution is observed for many wood species. But previous research reported 2 examples of Zelkova here that show the different shape of the distribution from a typical bell shape. At that time, the report was around 2000, There was no further investigation about this somewhat strange distribution. So our present research rediscovered the previous findings in collaboration with a traditional construction company. We measured the released strain distribution with strain gauge method. Here I show 3 examples of released strain distribution of zero cover logs. The unique distribution were found again, which was different from this typical distribution. And they had zigzag patterns more or less and seemed to have wide variations among trees. So we tried to confirm the characteristics of zero cover. We measured released strain of 63 logs. Here I would like to show the variations in the distribution. Each graph shows a released strain distribution of each zero cover log. Then we concluded that all the logs had unique distributions characterized by zigzag patterns and not always bell-shaped. Several previous studies also measured residual stress of other wood species using a lot of logs, but there are no studies that reported such a zigzag distribution. So it can be said that it is a characteristics of Japanese zero cover. So the next step is to clarify the origin of the distribution. Here I show the possible origins that can make the zigzag patterns of released strain. First, until here, I have been talking on the strain, not the stress. So to discuss the strain has to be converted to the stress by multiplying Young's modulus and released strain. But we have not measured the Young's modulus for each measuring point because there are too many measuring points. Also, the random existence of tension wood and base cell frequency and the occurrence of interlocked grain were thought to be the origin of the distribution of the released strain. So today I will not go into the details, but we have already examined these possibilities and for the moment concluded that the tension wood distribution is the most possible origin. So I'm going to show how the tension wood looks in the Japanese zero cover logs. In the left two photographs, you can see dark stripes in zero cover board. In the middle photograph, there are horizontal cracks that occurred due to the large dry shrinkage of tension wood. From these photographs of the board, we can estimate that even in a straight and vertical trunk, the tension would randomly generated through the growth of zero cover tree, like this light photograph. This is a cross section of the large stem of zero cover tree. So the tension would generate tensile stress. So eventually the random distribution would make the zigzag distribution of released strain. Here I would like to discuss the mechanism from the viewpoint of biomechanics. How does the zero cover tree form such a random distribution of tension wood? Probably when the trunk inclines slightly or branches become a little heavy, the zero cover tree responds more sensitively than other tree wood species by forming tension wood. So we don't know yet whether this is a mechanical adaptation. We also do not know yet if the residual stress distribution of zero cover has any mechanical significance to survive for tree. However, we can consider growth history and its relationship with tree form, tree shapes, and the residual stress distribution. So I will end my talk here. So finally, if I have a open question for you, if you know any tree species that frequently form reaction wood like zero cover tree, please let me know. So I have heard that acacia mangum is one of such trees, but we haven't been able to confirm this, and the released strain distributions of acacia mangum showed a very clear bell shape. So thank you for your cooperation in advance, and thank you very much for your attention.
Thank you very much, Dr. Matsueda, for the interesting presentation related to the growth stress in Zelkova serrata. And next, we will move to the third presentation that will be delivered by Dr. Rozaka Noviandi. Before we start the third presentation, I would like to introduce Dr. Rozaka. Dr. Rozaka got bachelor degree from Faculty of Engineering, Universitas Gadjah Mada, Indonesia, and for master and doctoral degree graduated from Tokyo University of Agriculture and Technology. His research interest is about geotechnical engineering, soil bioengineering, sediments, related disaster. He also already published many papers in international journal and proceedings. Dr. Rozaka will present the research on the effect of forest density on slope stability insight from flume experiment. Dr. Rozaka, time is yours. Hello, Dr. Rozaka. Hello, can you hear us? Hello, Dr. Rozaka.
Can you hear my voice?
Oh, yes, we can.
Sorry, previously I can't unmute myself.
Okay.
It seems something wrong with my Zoom. Okay. Just wait. Okay. Just wait a minute. Okay, can you see my screen?
Yes, we can.
Okay, can you also hear my voice?
Yes.
Okay, thank you. So, good afternoon, ladies and gentlemen. Please allow me to introduce myself. My name is Rozaka Andy, but you can just call me Andy or Andy. I'm from the Department of Civil and Environmental Engineering, Gadjah Mada. And today, I would like to present one of my research related to the effect of forest density on slope stability. Okay, I think you already know about landslide. Yeah, especially in Japan and Indonesia, we have a really high landslide frequency. So in a simple term, this landslide can be defined as a downslope movement of slope materials under gravitational action. This landslide can be found in hilly and mountainous areas due to extreme rainfall or earthquake. In last decades, about 7,000 rainfall-induced landslides occur globally, mostly located in Asia. Due to climate change, this landslide frequency are projected to increase by the end of the 21st century. If we look at the global landslide inventory, more than half of landslides occur in forested hill slope, as shown in this picture. Therefore, the presence of vegetation cover can potentially influence the occurrence of landslide. This initiation of landslide is important parameters for landslide risk assessment. Vegetation can alter landslide initiation as the roots reinforce soil structure that impact slope stability. These vertical roots here act on the basal shear surface, enhancing basal shear resistance, while these lateral roots bind the soil, preventing slope deformations, cracks, and delaying landslide. Through this mechanism, these vegetations can enhance slope stability by up to 30% higher. In addition to slope stability, vegetation roots is also the key for geomorphic processes of the slope. When the roots from neighboring vegetation stand overlap, they form a network of roots, here I define as root system. Therefore, previous studies found a reduction in landslide size occur as vegetation density increase associated with the root system. However, how vegetation density influences the size of landslide remains a question. Root system can also alter hydrological processes of soil. It can disperse or bypass and accumulate water. However, here, how changing in vegetation density influences this process is not fully understood. Therefore, I set a primary objective of this study to evaluate hydrogeomorphic controls provided by root system under different vegetation densities on landslide initiation, which has two specific objectives. First is to evaluate how vegetation density affects slope stability and how hydrological process changing due to root system. To achieve this objective, I developed flume apparatus with 1/70 scale consisting of the initiation or the slope and the deposition segment. I install nozzles above the flume to simulate the rainfall. I use non-cohesive sand with 10 centimeters of thickness to simulate shallow soil. I install net at the side of the flume bottom to create landslide boundary. To simulate root system on hill slope, I use piece or tomyo in Japanese because it can grow really fast. After 2 weeks, this piece had 25 to 30 centimeters of height, representing 18 to 21 meters of actual trees by 1/70 of geometric scale. In addition to their rapid growing capability, this piece was used to represent trees with taproot system with central large root that give rise to lateral roots. This root system was found in up to 73% of woody species. Because the growing characteristic of trees is represented by the ratio between low and above ground biomass, this piece with biomass ratio of 0.2 to 0.3, representing the growth characteristics of Japanese cedar with biomass ratio of 0.24 to 0.35. On the slope, the peas were grown for 2 weeks with even spacing. The density of vegetation was 50 to 4,400 stems per square meters, representing forests with 100 to 9,000 stems per hectare of density. The above ground was cut before the experiment. I then applied water from the nozzles with a constant intensity of 90 millimeter per hour. The time when landslide is initiated were measured. This experiment for each density conditions was repeated for 3 times. Now I'm going to show you the result of my observation. During the deformation process, I found that both initial cracks, formation of new cracks here, and before the landslide were located at the gap between vegetation. These findings agree to previous studies that gap between vegetation representing the weakest areas of the slope. Now I'm showing here X is vegetation density, Y is the timing of the crack formations, timing of landslides, and the maximum deformation. As you can see here, as vegetation density increase, the time for the crack formations also increase. However, if you look at the maximum deformation here, it is getting lower compared to the moderate density conditions. This condition might be associated with root reinforcement. Investigate this characteristic of root reinforcement, I calculate root architecture as two variables. One is overlapping length and another one is overlapping percentage. I also calculated root reinforcement notasi as representing values of root contributions as additional cohesion on the soil. As you can see in this figure, the x-axis is the overlapping length and the y-axis is root reinforcement. As overlapping increase, root reinforcement exponentially increase. Although for the same densities, the value of overlap and reinforcement is different, but exponentially correlated. This indicates that overlap characteristics is one of the key indicators for explaining root reinforcement. Now, I'm showing how root architecture representing overlap percentage and overlap length is different. Generally, overlap percentage is increasing but the overlapping line is decreasing at the high density, which is possibly associated with the vegetation competitions at the high density conditions, limiting the root growth. How this vegetation growth and competition possibly affecting for landslide characteristics. Now I'm showing the overlapping line here in the x-axis and the maximum displacement at y-axis. Here we can see that as the overlapping line is increasing, the maximum displacement also increasing. The maximum displacement is higher at 1100 stems per hectare than 4400 stems per hectare, which is related to the limitations of high density conditions. The interactions between neighboring plants is the key for the formation characteristics of the slope. However, although I found that both overlapping and cohesion follow vegetation density, the size of landslide in these illustrations doesn't follow vegetation density. It decreases as vegetation density increase, which agrees to previous studies, and increase for the density exceed 400 stems per square meter. And this condition is possibly associated with internal hydrological processes within the soil matrix. Here I'm showing water distributions over the time from 5 minutes until collapse. As you can see here, the red color here, the color representing the metric water content of the slope. The red indicates high saturations. And as you can see here, that the high density conditions, in here, the high density conditions form saturation quicker than the low density conditions. And this behavior extending until the slope collapse. Characteristics is possibly associated with the development of root network, providing preferential flow, which also occur at the 5 minutes after the rainfall application. Now I'm showing the time of saturated areas here in the y-axis versus vegetation density in x-axis. As you can see, the time for saturation increased from low to moderate density. However, the saturation is quickly formed at the high density conditions, which is possibly associated with bypassing flow provided by root network. In addition to changing the time and area due to the root systems, the saturation are extend for the lower hill slope to the upper hill slope. As you can see in this graph, that the saturated areas on dense conditions is extended until the upper hill slope. Therefore, areas with low shear resistance under low density conditions is possibly, the areas with low shear resistance under high density conditions is possibly extending, causing larger areas on high density condition. To summarize here, I found that the vegetation density influenced saturated areas timing, size, and the length of the landslides via root overlap. Low vegetation density increased the size because of low root reinforcement, whereas high vegetation density increased the size of landslide because of the extensive saturated areas formations. Therefore, I suggested that an optimum conditions of forested hill slope exist for minimizing landslide size. In addition to that finding, I also found that the vegetation density influences how far landslide sediment move. As you can see here, as the increase in vegetation density enhance the mobility of landslide sediment. But at the very high density, the mobility is kind of reduced. It is really interesting. I'm not going to talk about this in today's webinar. And I think that's all for me. Thank you very much for your kind attention.
Thank you very much, Dr. Rozaka, for the very interesting presentation related to the effect of forest density on stability insight from plume experiment. And ladies and gentlemen, and next we arrive in the last presentation by Mr. Kevi Indra, Master of Science. First, I would like to introduce Mr. Gevri. Mr. Gevri finished his special degree from Andal University, Padang, Sumatera, and got Master of Science from Faculty of Forestry, Universitas Gadjah Mada. His research interest is in critical wind assessment and wind risk model using forest scale model, and then development of non-destructive models to estimate wood properties and wood quality assessment to support breeding pipeline. Mr. Gevri will share findings on parameterization validation of the forest scale model to determine the critical wind for damage of different eucalyptus clone. Mr. Gevri, time is yours.
Okay, can you hear my voice clearly, Dr. Fani?
Yes, we can.
I will start my presentation.
Yes, please.
Okay, let me okay. Okay, I will start, Dr. Fani.
Yes, please.
Okay, good morning, good afternoon, everyone from Indonesia. First, I would like to say thanks to the committee for giving me the opportunity to deliver this result to all of you. Before starting the presentation, I would like to introduce myself. My name is Jeffrey Indra Huta Barat. I'm currently an employee working in Wood Technology Department in Fiber R&D Business Unit in April Company. Today, I would like to share with you the result titled the parameterization and validation of the forest scale model to determine the critical wind speed for damage of different eucalyptus clones. So this is the paper that we have published in Forest Ecology and Management. And this paper align with the topic that I'm going to present to all of you. But here I would like to say thanks to the April management and all people involved, including the Dr. Fani Hidayati and Dr. Berry Karina for supporting this research and this publication. So to start, I would like to tell you that currently wind damage to our eucalyptus plantation is becoming a major disturbance, producing negative impact to our industry company due to the reduction of the wood productivity in our plantation. And wind damage itself causes the tree breakage and uprooting in our plantation. And based on our forest inventory data, according to wind damage incident, we found that the high level of wind damage happened from 1.5 to 3.5 years old, with the total of wind damage from 7 to 15% by area in eucalyptus plantation, and significant increase at 2.5 years old. So in order to mitigate the wind damage incident in our plantation, we calculate the critical wind speed using the forest scale model to determine genetic material resistant or susceptible to wind damage. Forest scale model is a hybrid mechanistic empirical model to calculate the risk of the wind damage to our plantation. Mechanistic model is to simulate how the physical force, like wind, interact to the tree structure, such as the crown, stem, and root. And empirical model is the statistical relationship derived from observed data. And we choose this model because this model was successfully adapted to calculate the wind risk to conifer and broadleaf forest in many countries in Europe, North America, and East Asia. Besides that, we also need to measure the wind speed data. By having the wind speed data, we could calculate the probability damage in our plantation and also to validate our forest scale model. And then this is the schematic of the critical wind, the equation of the critical wind speed using the forest scale model. So this is the critical wind speed for stem breakage, and this is the critical wind speed for uprooting. So to calculate the critical wind speed, first we need to measure the tree spacing. In general, wider tree spacing increase the wind exposure, and in the same time with potential to increase the tree diameter. And then we also need to measure the gas factor. This is related to the wind loading exposure. And then we need to measure the stem and the crown mass. This is related to the effect of the gravity force. And then we need to measure the tree height and the diameter. Tree height, as we know that the taller tree experience increased wind loading, and the diameter is related to the resistance to breakage. And then we also need to measure the modulus of rupture. So modulus of rupture, or MOR, is the maximum stress the wood can withstand before breaking in the bone bending moment. And then we also need to measure the CREF parameter. This parameter is the key parameter in forest scale to calculation the critical wind speed for uprooting. And then this is the experimental design to parameterize the forest scale model. So first we selected 2 eucalyptus clone based on the actual damage in our plantation. Clone A has a low wind damage incident, and then in clone B is a high wind damage incident. And then we sampled those eucalyptus clone at the same age, and they were planted with the same spacing. In total, we sampled 27 trees per clone based on the 3 diameter classes: dominant, codominant, and subdominant. So we parameterized the forest scale model by measuring the 3 characteristics: wood strength and uprooting resistance. So this is the schematic of the tree pulling experiment to determine the uprooting resistance. So we adapted this schematic of the tree pulling from the Rika and Nicole, and also Nicole et al. 2006. So here we selected 3 trees. So this is the target trees, this is the anchor trees, and this is the power wind trees. So here we need to cut the target trees at 1.1 meter high. So this is the related to the safety reason during the pulling test. And then we install the pulley, 3 pulley, load cell, dynamometer, and also the power winds. And then we pull at the lower height here to uproot the tree rather than to pick the tree. And then we pulling this tree, the target tree, until the tree is uprooted like this picture. And then the software will record the maximum resistance moment for uprooting. And then this is the 3 characteristic measurement. So we need to measure the diameter at 1.3 meter high, and then crown diameter, tree height, crown depth. And then we need to measure the diameter each meter along the stem to calculate the total stem volume. We measure the crown width, and the last one we measure the tree stem at 20% of the total tree height to obtain the greenwood density and to calculate the total stem width. And then this is the modulus of rupture and modulus elasticity measurement. Here we use near infrared to estimate MOR and MOE. So we collected the wood brush at DBS position, and then we granted the wood brush to be the small size. We call it here the wood sawdust, and then we scan the wood sawdust using the infrared, and then we collected the spectra, and we use the spectra to predict the MOR and MOE. Currently, we already have a good near model to estimate MOR and MOE. And then this is the flowchart of the forest scale model calibration. So this is the all input parameter required to run the forest scale model to calculate the critical wind speed. And this is the output parameter from the forest scale model. So we measure the three characteristic, and then we measure the wood strength, and also we measure the uprooting resistance. So for some parameter, we could collect it from the forest inventory database, and for the some such as crown and stem width and the CIREC parameter, we use empirical model to provide those parameters. And we input all parameters to forest scale model to calculate the critical wind speed at 40 meter height for each compartment in our plantation. And then we measure the maximum wind speed to calculate the damage probability for each compartment in our plantation. And then we validate the damage probability of this compartment against the actual damage happen in our plantation. And then this is the model forest scale model validation. So here we use the ROC and AUC to perform to determine and evaluate the model performance and the threshold based on the conversion matrix. So the conversion matrix is a table that visualize the classification model by comparing the predicted value from the forest scale model and the actual value of the wind damage. For example, true positive means the model and actual data indicate damage in the compartment, and true negative means the model, our model, and actual data indicate no damage in our plantation. So the ROC curve will automatically select the model and also the damage threshold. For example, if the AUC 0.5 means that the model no discrimination in damaged and undamaged compartment. If the AUC equals 0.8 means the model could discriminate damaged and undamaged compartment. So this is the first result. This is the CIREC parameter based on the tripling experiment. So as I mentioned before, that the CIREC parameter is the main parameter in forest scale model to calculate the critical wind speed for uprooting. So here we could see in the table here that stem width has a significantly correlation with the maximum resistance moment for uprooting, and this is the slope of the regression for each clone that we use or we classify as a CIREC parameter. And here we also try to analyze the CIREC value between two eucalyptus clone, and we found that there's no significant difference in CIREC value for two clones. And then this is the new parameterization for clone A. So this is all parameter that we need to measure, and this is the all formula that we need to calculate to run the forest scale model to calculate the critical wind speed for clone A. And this is for the formula or characteristic for clone B. And then this is the mean resistance to breakage and uprooting for clone A and clone B calculated by forest scale model. So mean resistance to stem breakage and uprooting is how much force that we need to uproot or to break the tree. So based on this table, we could see that the clone A has a higher mean resistance to breakage and mean resistance to uproot compared to clone B. It means that we need more force. We need more force to uproot and to break the tree in clone A compared to clone B. And then this is the critical wind speed for clone A and clone B calculated by forest scale model. So on this graph, we could see that first the clone A has a higher critical wind speed for both stem briquettes and uprooting compared to clone B at each age. And then the second one, we could see that in clone A, the critical wind speed for stem briquette is higher than uprooting at all age. It means that clone A is more resistant to briquettes compared to uprooting. And meanwhile, the clone B has a slightly higher critical wind speed for uprooting compared to briquettes. It means that clone B is more resistant to uprooting than briquettes. So the results show opposite between two clones. And the last one, we could see that the critical wind speed for stem briquettes and uprooting decreased with an increase of the tree height for both clones. It was due to the higher taper of the other trees. So higher tapers means that the tree grow taller related to their density, their diameter. So in general, higher taller tree experience increase the wind loading. And then this is the result of the validation of the four-scale model using ROC. So based on the ROC and AOC, we could see that the model was successfully discriminate between damaged and undamaged compartment with the AOC higher than 0.7 and accuracy higher than 75%. High accuracy means the model correctly classified damaged and undamaged compartment over 70% of the time. So from the result, we can conclude that the model has a good performance to classify the damaged and undamaged compartment based on the probability damage and actual damage in our plantation. So this is the use of the four-threshold critical wind speed for tree improvement selection. The beginning of the presentation, I mentioned that significant high level of wind damage occur at 2.5 years old. So here we use the critical wind speed parameter to rank genetic material resistant to wind damage. Based on this table, we could see that the clone A at 2.5 years old has a higher critical wind speed for stem briquettes and uprooting compared to clone B. It means that clone A is more resistant to briquettes and uprooting compared to clone B. And this findings aligns with actual damage in our found in our plantation. It means that clone A with higher critical wind speed will have a lower tree damage, and clone B with a low critical wind speed will have a lower high actual damage. So we use this information to classify or to rank genetic material resistant to wind damage. So this is the conclusion of this research. First parameterization of the four-scale model was done for the first time in Indonesia for eucalyptus plantation by measuring tree characteristic, wood strength, and uprooting resistance. DBS and tree height are important factors associated to tree briquettes and uprooting. Stem mass, the best predictor of the tree pulling resistance growing in Indonesia based on the tree pulling experiment. Four-scale model was successfully validated to discriminate with damaged and undamaged compartment, and the critical wind speed calculated by four-scale model can be used as a tool for tree breeder and forest manager to select genetic material resistant to stem briquettes and uprooting due to the wind. And the last one, critical wind speed of the genetic material is recommended as a new parameter to select eucalyptus clone resistant to wind damage. I think that's all from me. Thank you.
Thank you very much, Mr. Gevi, for the next presentation related to the parameterization validation the four-scale model to determine the critical wind for damage. Ladies and gentlemen, all presenters have been presented their topics. Therefore, we will come into the discussion sessions. For the first chance, please two questions for the participant from this room. You can raise hand if Anyone want to ask? Okay. The first is Miss uh, Yulia Amirul Fatah.
Yes.
Okay. Please, and please, where are you from also?
I'm from Universitas Brawijaya.
Okay, thank you. Please.
Okay, thank you for the chance. Good afternoon, everyone, and all distinguished speaker. Thank you for all the presentation. I'm Yulia from Brawijaya University. I want to deliver question for Mr. Rozaka, the third speaker. Currently, I'm studying on the hydromechanical effects of vegetation on slope stability, which is really related with your research. And I found new insight from your presentation. And my question is about how can you make sure that your research using pea plants that it will represent the role of forest in your study. As far as I know, different vegetation types have distinct characteristics in their roots, stem, and other structure, which might influence their mechanical effect. So this is all my questions. Thank you.
Okay, thank you very much. Maybe Mr. Razak can answer directly.
Okay, check.
Yeah.
Yulia, can you hear my voice?
Yes, it's clear.
Yeah, I agree that different vegetation types might have different effects on slope stability, right? For example, if we have deep penetrating roots as compared to the shallow roots, the effect will be different as deep penetrating roots may be more effective in maintaining the slope stability. Yeah, I think it's quite difficult to answer because, yeah, of course it is different. But what we found here is we found that the key for slope stability is the density, and to prove that the density is matter in terms of slope stability, actually right now we conducted kind of numerical simulation, and we found similar pattern that there is maybe an optimum density for slope stability. Yeah, because the objective of this study is to kind of simulating the effect of actual trees, but instead we try to isolate the effect of density. So yeah, it's quite difficult to answer, I think.
Yes, okay, thank you for your answer. But in my opinion, what kind of I'm studying before that it might be more suitable when you can use like leguminaceae species, I think, because this is quite popular for the slope stability reinforcement, like in the hydro seedling. Nah, this is like this kind of something that it can be in my opinion, this is maybe more suitable because the root system it's maybe more strong than the P plants that you use in your
Okay.
study. This is my opinion, but so if you're using the P plants, is that any studies before that it is modeling the P plants before in your study? I mean,
Sorry, I think I should emphasize why I use P is because of scaling at first.
oh yeah.
So
Oh,
as
I
you know
see.
that our slope is 1/70. It means that 70 times smaller than the actual hill slopes. If we use trees that, let's say, that have the similar strength to the actual trees, it will be overestimating the effect of reinforcement, because we have smaller models with that generate smaller landslide, which means smaller mass. So we need to find suitable plantations that fits our scale, and we think that this piece is kind of suitable for this scale. Also, another considerations why we use P is because of the timing. You know that
Yes,
this
I
P
see.
is really
Faster growing,
fast to
fast.
grow.
Yes.
Yeah.
Okay.
Yeah, but if you know, but if it is different or not, yeah, I agree that it is different.
Yes. Yes.
For example, maybe if we use different traces, the response can be different, but yeah, maybe the optimum density health can be shifting depending on the vegetation density. Yeah, maybe in the future, we are going to test the effect of this density on slope stability in different root architecture.
Yes.
Yeah, can be. but yeah.
Very good answer.
Okay.
Yeah,
Thank
thank
you
you
for the
for your
answer.
question.
Yes.
Okay. Okay, thank you very much, Mrs. Julia, for the question and discussion. And the next, is there anyone who want to ask the presenters in this room? Okay, if not yet, I will move to the chat box. There is any three question from the participant. The first is from Mr. Trisno Budi Hutomo from Ministry of Forestry. From Ministry of Forestry, he asked, the first question is for Dr. Matsuo Ueda. Is there any relationship between residual trees during manufacturing processes with product durability? And the second, I think for Mr. Jeffrey, critical wind speed could be implemented at private forest. So it need information, critical wind speed from all species, economical wood species. Please, Dr. Matsuo Ueda, to answer the question of Mr. Trisno.
Yes, thank you for the question. So, actually, I'm not sure what kind of durability does Mr. Futomo imagines, but in terms of durability, I think there is no relationship between growth stress, between digital stress and the durability. So if any comment from Mr. Fumoto, I will be welcome.
Dr. Fani.
Tes. Okay. Okay. I'm sorry, I have a trouble here. Okay, thank you very much, Dr. Masuo, for the answer the question of Mr. Krishna. And the second one, we move to the Mr. Jeffrey. Mr.
Okay. Okay, Dr. Fani. So I would like to try to answer the question from Hutomo. So the question is about the critical wind speed could be implemented at the prepared forest. I will say yes. Yeah, but my suggestion is what's the main issue that you are facing now in your prepared forest? If related to the wind damage, what kind of the type of the wind damage? It could be the stem rickets and or uprooting. So if the main issue is the stem rickets because of the load, a lot of work, a lot of parameters to be measured. So I think yes, so you need to measure a lot of parameters that I explained previously, and then we, based on the calculation that I saw, we could calculate the critical wind speed for your prepared forest. I think that's the answer for the question, Dr. Pani.
Thank you very much, Mr. Jeffrey, for the answer the question of Mr. Krishna. I hope it already answered the question of Mr. Question Mr. Krishna. And the next question, okay, in the room we have Mrs. Anissa. Mrs. Anissa, can you hear me? Mrs. Anissa? Okay, okay.
For the okay, we want to ask you about the topic that you share with us. First, what causes land with vegetation to trigger landslides? Is it influenced by the type of trees or by the soil? Or are there other environmental factors? How do landslides?
And then how do landslides in vegetation covered area compare to those in areas without vegetation? Thank you.
Okay, okay. Mrs. Anissa, where you come?
We are from Universitas Gadjah Mada.
Okay. Okay.
Yes.
I think this question is for Mr. Rozaka. Dr. Rozaka, maybe you can directly answer the question.
Yeah. Sorry if I'm not mistaken. The question is about. Could you repeat your question, please?
Okay, the question is about what causes plant to trigger landslide influenced by trees or the type of soil or other factors.
Oh, okay. I think the first question is related to the cause of landslide, right? So in theory, there is two factors cause landslide. The first is triggering factors. It is external stimulus, the slope, such as rainfall, earthquake, and then human activities. And the second factor is controlling factor, such as topography, soil types, and possibly the vegetation itself. So in terms of vegetation, it can exert both positive and negative impact on the slope. The first, if we talk about the positive effect, the root itself can increase the matrix suction or simply can reduce water content on the soil, transpiration. So it can make the soil, it can reduce the water content on the soil and the slope more stable. The root itself can enhance the cohesion on the soil. So if we know the cohesion is a kind of the ability of soil particles to stick together. So more cohesive, it means more stable. And the roots can enhance these cohesions. But also the canopy itself can retain water during the rainfall. So it reduces the raindrop to the soil. But talk the negative effects, the weight of vegetation can exert load on the slope. So yeah, in short, if we talk what cause landslide, there are several factors. The first is triggering factors such as rainfall and earthquake, and controlling factors such as the topography types and vegetation types. If we talk about vegetation, it can enhance or reduce the stability. Yeah. Is it sufficient for you?
Is it okay, Mrs. Anna? It's already enough?
Yes, enough. Thank you for the answer, sir.
Okay, thank you very much. And the next question is from Mrs. Anna Len Hansen.
Hi, thank you for the opportunity to ask a question. Can you hear me okay?
Yes, we can hear.
It's a question for Dr. Yamamoto, the first speaker. I just wondered, what are the unknowns or the knowledge gaps you briefly mentioned that exist in the water potential model? Thank you.
I'm sorry, where do you come from, Mrs. Anna?
Aberystwyth University in the United Kingdom in Wales.
Okay, thank you.
Thank you.
Yeah, and please, Professor Yamamoto.
Yes, I hear you. So my question, your question. So please make a question again briefly. You mean what do you mean attention?
I asked what are the knowledge gaps or the unknowns in the water potential model you mentioned?
So tensile model, tension wood model.
It was about the water transport systems.
Transportation system, yeah.
The water potential model.
Tension model. Tension model. Not the tension word.
But water,
water potential.
Yeah.
Sorry. So water potential is now nowadays many people believe the role of water potential to transport the water from root to the for example leaf. So some people doesn't believe such a mechanism. So now under controversy, still controversy. But the theory of water potential model is very effective to explain the mechanism of water transportation, physical point of view. So how about do you think about the water potential model to explain the mechanism of water transportation from root to the leaf? You believe or not believe, Dr. Hansen?
I agree with you that it's the generally accepted model, and that is what we are taught at school. But you said that there is still some controversy, so I wondered why that has arisen, why that occurs?
So there are several models to explain water transportation. Still, we have some kind of different models, not only water potential theory. So, my opinion, this is still controversy. So we had better continue to discuss about this model, not only from the physiological, but also from the, for example, the property of water, physical property of water and the structure of the xylem. Not yet finished, I believe. Thank you.
Thank you very much.
Thank you very much.
It's enough, Miss Annalyn.
Yeah, great. Thank you.
Okay, thank you very much for the question. And the next for Dr. Barry Gardiner, please.
Hello, sorry.
Yeah.
I'm on my phone, and
Yes.
I really like the last question because I actually am not convinced we still know how trees transport water. I think this is a really open topic for for research, and I'm not a great believer in the water potential theory. So I think the last speaker, I don't know, I've already forgotten your name, I'm so sorry. I think your question was very valid. Is that what you're working on? Are you working on water transport in trees? But personally, if you're an ambitious young scientist, I think this would be a topic to really work on. Thank you. Nice talk, by the way.
Thank you very much, Dr. Barry. And the next we will move to the chat box, and there is any question, okay, from Professor Imam Wahyudi, and already answered by Dr. Barry Gardiner. Actually, Barry Gardiner is a supervisor also of Kefri Ida Huta Barat. Thank you very much, Dr. Barry. And the next, the question from Jennifer Lopez Ortiz. When you this is a question is for Professor Yamamoto. When you discuss how transport water to their upper part driven by water potential, it made me wonder about the situation in extremely cold environment. Here in Finland, temperatures often drop below zero, and water in the xylem could freeze. How do plants manage to maintain water transport in this condition? Does the water freeze completely? And if so, what mechanism allow plants to continue moving water to their stem and branches during after freezing? Please, Professor Yamamoto.
Okay, very suggestive opinions. This problem is still very hot discussion in the field of the tree physiology. And so I think the water potential theory is one of the best explainable theory. But so not only water potential theory mechanism, but also other mechanism is maybe very important. So we will still discussing. We had better continue to discuss about it. Very hot discussion, I expect. Thank you.
Okay, thank you very much, Professor Yamamoto. And I think there is one question from Sapki, Mr. or Mrs. Sapki. Did Forest Gale model had validated to compartment that planted many clones or composite clones? Is it possible for mapping clones that for planted in specific area? This question is for Mr. Geoffrey. Please, Mr. Geoffrey.
Okay, I will answer sub-key question. So the first question about the did Forest Gale model had validated to the two compartment that planted with many clones or composite or mixed clone. So actually not yet. So Forest Gale model is not validated to the clone or mixed clone planted in the compartment. But this information is very important. So if we already have mentioned the many clone and we already have the critical wind speed on its clone, we can plant them in the same compartment or the same place, so we can reduce the mitigation by plant the mixed clone in the compartment. The clone will have a higher critical wind speed. So we need to measure what we call the single individual for each clone, individual compartment clone planted in the compartment. And then the second one, any possible for mapping clone based on that for planted in the specific area? Yes, actually yes. So if we have the critical wind speed for its genetic material, so we can inform to the forest manager to plant it, for example, the clone with a lower critical wind speed at the specific area means the area with low wind exposure. So to implement that situation or that strategies, we need to understand the wind behavior in our plantation. I think that's the answer.
Okay, thank you very much, Mr. Gevi, for the answer. And the next, if any more question from the audience. Okay. Professor Imam Wahyudi from IPB University, please.
Thank you, Dr. Fani. If we have still time, I want to ask to Mr. Jeffrey. Yeah. I want to know why the model use the MOR, because it's still tree, not the lumber or timber. So in my opinion, maybe the thickness of the bark is very important. So why in the model they are not considered about the thickness of the bark? Thank you.
Okay, thank you very much, Professor Imam. Please, Mr. Gevi.
Okay, I will answer the question. So in the in the forest scale model, there's a mechanistic model. So mechanistic model is to simulate the what we call the physical force like wind to the tree structure. So because we're talking about the critical wind speed to stem breakage, so it will related to the resistance to breakage. There's a parameter, we call it MOR. So MOR is important parameter to measure the resistance to breakage. So this is the wood mechanical. So here we use the wood MOR to determine the resistance to breakage. And then in the mechanical model, when the wind come to the push the tree, so it will produce the wind force and also the gravity force. So the principle is when the wind force and gravity force higher than the resistance, the stem resistance, so the tree will break. So it's not only about the MOR, but also the diameter and also the knot factor. So that's the all parameter to measure the resistance to breakage. So MOR also one of the important parameter to measure the critical wind speed for stem breakage, because related to the wood mechanical. I think that's my answer.
Okay, thank you.
Okay, thank you very much, Prof. Imam. And the next question will be the last question from the chat box. From Mrs. Rahmi Mauladini. The question is about I would like to ask related to the tension wood. Does the presence of tension wood increase the strength? I think this question is for Dr. Matsuo Ueda. Please, Dr. Matsuo Ueda.
Yes, thank you for your question. Yes, as you said, basically the presence of tension wood will increase the tensile strength, not only the tensile strength, but the this is due to the highly oriented cellulose microfibril with high ratio in xylem, but the compressive strength will be decreased because cellulose microfiber is not so resistant to the compressive stress. Is it clear for you?
I hope Mrs. Rahmi, it's already enough, yeah, Mrs. Rahmi. Okay, thank you very much, Dr. Matswa. And ladies and gentlemen, we are just about of time. Thank you all for a truly engaging and insightful discussion. And to briefly recap, we have explored and discovered the significant information. First is about the history of the plant evolution, that plant biomechanics can learn evolution and how tree can support their giant stem. And then the plant utilize mecha and physics for their survival, and what plant biomechanics should go and do. And the next is about the second presentation about the keaki trees, how the importance of the Zelkova serrata trees in Japan, and there is any unique distribution of a release strain possibility due to the tension wood in keaki trees, and we have to understand too that tension wood can exist in the straight stem also. And for the next, related to the third speaker, that vegetation density influence saturated area timing, size, and length via overlapping, and low vegetation density increase the size because of low reinforcement, whereas high vegetation density increase the size because of extensive saturated areas formation, and an optimum condition exists for minimizing land slide size. And for the next presentation, the last presentation, that the wind speed calculated by the forest scale model can be used as a tool for tree breeders and forest managers to select genetic material resistant to leakage and uprooting due to the wind. And critical wind speed of the genetic material is recommended as a new parameter to select eucalyptus clone resistant to wind damage to prevent the loss of the wood in the field. And I would like to express my deepest thank you to our speaker, Professor Yamamoto, Dr. Matsuo Ueda, Dr. Rozaka, and also Mr. Jeffrey for the time sharing knowledge in this webinar. And to our audience, thank you for your thoughtful question and attention in this webinar. We hope that this webinar will give the information of update research on plant biomechanics, especially in Asia. Once more time, thank you very much, and we are looking forward to seeing you again in next 2 weeks in this second webinar series. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Halo Pak Nuk, sehat selalu.
Ya, terima kasih. Baik, Prof. Imam. Photograph? You don't take photograph?
Thank you very much, Dr. Fani Hidayati, for leading today's session with such a fruitful and engaging discussion. We truly hope that knowledge shared today will be beneficial and inspiring for all of us. I would also like to kindly remind all participants to fill out the attendance form through the links that has been shared in that box. Ladies and gentlemen, as a form of recognition, we would now like to present the certificates of appreciation to our distinguished speaker and our honorable moderator. Let us begin. For the first, to Professor Dr. Hiroyuki Yamamoto from Nagoya University, Japan. May we kindly invite the committee to display the certificate. Thank you. Professor Dr. Hiroyuki Yamamoto, please allow us to take a brief documentation photo.
Okay, thank you very much.
Thank you very much, Professor Dr. Hiroyuki Yamamoto. For the second, Associate Professor Dr. Miyuki Matsuo Ueda from Kyoto University, Japan. Committee, please display the certificate.
Thank you very much.
Wait a minute. Associate Professor Dr. Miyamatsu Yuda kindly prepare for documentation. Thank you very much, Associate Professor Dr. Miyuki Matsuyoda.
Thank you.
Auditor to Dr. Saka Noviandi from Universitas Gadjah Mada, Indonesia. Committee, please present the certificate. Dr. Rozaka Noviandi, can you prepare for the documentation? Thank you very much, Dr. Rozaka Noviandi.
Thank you. Thank you very much.
Order to Mr. Kefri Hutabara MSc from Asia Pacific Resources International Limited April, Indonesia. Mr. Gendra Hutabara MSc, kindly prepare for the documentation.
間違えた。みんなに送っちゃった。間違えた。
Thank you very much, Jeffrey Indra Hutabarat, MSc. Finally, to our honorable moderator, Dr. Fani Hidayati from Universitas Gadjah Mada, Indonesia. Committee, please display the certificate. Dr. Fani Hidayati, can you prepare for the documentation? Thank you very much, Dr. Fani Hidayati. Ladies and gentlemen, now we will moving on documentation session. So please everyone turn on the camera. Okay. 1, 2, 3. One, two, three. Okay, thank you very much, ladies and gentlemen. The documentation session is now completed. Ladies and gentlemen, we have now come to the end of today's webinar. I would like to sincerely thank all of our distinguished speakers, our honorable moderator, all participants, and the entire committee for your contribution to the success for the first session of the webinar series 2025, brought to the 11th International Plant Biomechanics Conference 2026. Can you remind you that our second session for the webinar series will be held on October 9, 2025. We look forward to welcoming you again for that session. And please don't forget, the highlight of this journey will be the 11th International Plant Biomechanics Conference 2026, which will take place in Yogyakarta, Indonesia on August 23 until 28, 2026. We hope to see you all there. Now, as we officially close today's event, may we kindly invite the committee to display the information about the upcoming conference in 2026 on the screen. Thank you very much and have a wonderful day ahead. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much,
Thank you very
everyone.
much. Thank you.
Thank you.